if you talk about quantum physics, we cannot talk about quantum physics without him. He has spent a lot of time in Pakistan, and I'm proud to be one of his PhD graduate, because he was also my supervisor, and I completed my PhD under his supervision. And during that process of supervision under his guidance, I learned a lot. And that training not only helps me in my academic and professional research career, but also in the administration as well. So thank you once again, sir, for being here. It's really a great honor and pride for us that you are here. And if somebody is interested to know the quantum physics and the mysteries behind it, he is the only person who can satisfy your levels, because I know there are so many questions you always wanted to ask. And I remember last time a talk was organized on quantum computing, I guess, and it was delivered by Dr. Shahid Kumar. He's also present here. And there were many queries and curiosities, even from those people who are not quantum physics background, who don't have any quantum physics background, and they are still here. Maybe they can also ask these questions to satisfy themselves. So it's again a great pride for us that Professor Suhail Zubairy is here, and this is the time the students can ask those questions related to quantum physics, because this talk is going to be very general talks. So I hope you will understand not only, but also you, whatever queries, whatever curiosity regarding this quantum physics concern, so you can ask. This is the right time to satisfy your levels of understanding. Once again, thank you, sir, for being here. I will not take much time between you and this audience, because they are still waiting for your talk to be delivered. Thank you. Thank you once again.
Thank you, sir, for your warm and insightful words. And now, with that, we move to the most awaited part of today's event, the discussion on the mysteries of quantum mechanics. Quantum mechanics, strange, puzzling, and yet incredibly powerful, is the science about the behavior of matter and energy on the atomic and subatomic scales. It is the science of the unseen, the uncertain, and the unbelievable. In this realm, particles exist in many states at once. Time and space behave unpredictably, and reality itself seems to shift with our observations. To help us navigate this fascinating terrain, we are privileged to have with us a highly accomplished speaker. Allow me to introduce our distinguished guest, Professor Dr. Muhammad Suhail Zubairy. Professor Zubairy's research interests include quantum optics and laser physics. He has been interested in quantum optical applications to quantum computing and quantum informatics. He is the co-author of 2 books, one on quantum optics and the other on quantum computing devices. Recently, he published a book on quantum mechanics for beginners. Professor Zubairy received his PhD from the University of Rochester in 1978, working under the supervision of Professor Emil Wolf. He held research and teaching appointments at the Optical Sciences Center of the University of Arizona and the Center of Advanced Studies at the University of New Mexico before joining Quaid-e-Azam University, Islamabad, Pakistan in 1984. He served as the Professor of Electronics and the founding chairman of the Department of Electronics at the Quaid-e-Azam University. In 2000, he joined Texas A&M University, where he is presently a university distinguished professor in the Department of Physics and Astronomy and the holder of Munner-Lin Heap Chair in Quantum Optics. He has received many honors, including the Wills E. Lamb Award for Laser Science and Quantum Optics, Alexander von Humboldt Research Prize, the Outstanding Physicist Award from the Organization of Islamic Countries, the Abdus Salam Prize in Physics, the International Khwarizmi Award from the President of Iran, the Orders of Hilal-e-Imtiaz and Sitara-e-Imtiaz from the President of Pakistan, and the George H.W. Bush Award for Excellence on International Research. He is an elected member of the Pakistan Academy of Sciences and a fellow of the American Physical Society and Optical Society of America. It is truly an honor to have such a learned personality among us today. Ladies and gentlemen, please join me in warmly welcoming Professor Dr. Muhammad Suhail Zubairy to the stage to deliver his talk on the mysteries of quantum mechanics.
Last one.
This is two. Okay, so first of all, a great thanks for inviting me to give a seminar here. I had been associated with this wonderful center, which has now emerged as one of the top universities in the country for many years. And I have known many colleagues from that time. I'm particularly gratified or even proud to be introduced by Dr. Sajid Qamar. It is not just Dr. Sajid Qamar who was once my student. There are several people in the first row like his wonderful brother, Dr. Shahid Qamar, and some others in the audience, Fazl Ghafoor and others and of course there are a lot of my grandchildren, intellectual grandchildren in the audience, those who were taught by these wonderful colleagues. The only negative point I can see in all of this is that it makes me feel very, very old. You know, when the rector of a university says that I was his thesis supervisor, that must mean to all of you how old I must be. But fortunately, I'm still quite active and really enjoy the things that I would like to share with you. So what I would like to talk about here today is some mysteries of quantum mechanics. I mean, quantum mechanics, as we all know, we are celebrating 100th year of its birth this year. It has been one of the most successful theories in the human history. I mean, after the passage of 100 years, there is not even a single phenomenon which is in violation with the predictions of quantum mechanics at a microscopic scale or at a macroscopic scale. But when you look deeper into it, you realize that it's a very mysterious theory. It represents a universe which is almost incomprehensible. And I'll give you some glimpse of that. Of course, you know, talking about it would require a very long time, but I would like to give you a glimpse of how mysterious this world is, a world according to quantum mechanics. So quantum mechanics has seen many different phases. I would like to talk about only one very small aspect of it and gradually build upon it. The modern interest in quantum mechanics and quantum technology that we see all around ourselves in some sense goes back to this paper, which was published in 2018 by a group in China led by Jianwei Pan. He is now almost like a national hero in China. The experiment that they had done was through satellite, a satellite named Meteus, named after one of the great optics person in China, ancient optics person. Through this satellite, they communicated within China over a distance of 2,500 kilometers and between China and Austria, 7,600 kilometers, in such a way that the communicated message was completely secure. So there was a secure intercontinental communication that was carried out. Now, by the way, Austria was, the message that was sent was between Jianwei Pan here in Zhenglong in China to Anton Zeilinger in Graz in Austria. And, Zeilinger was Pan's PhD supervisor. So that was sort of the connection. But this experiment, I mean, typically when scientists work on a research problem, they publish it in a journal, only the scientific community takes interest. outside, and particularly politicians almost never read journals like Physical Review or Physical Review letters and identify one good paper from another. But this paper was a very unique paper in the sense that it attracted immediate attention of politicians, people sitting in the White House of United States. And as I once mentioned to John Vaipan happens to be a good friend. So I mentioned to him that in any situation where three words combine together, security, satellite, and China, it is bound to generate a lot of interest in Western capitals, particularly in Washington. So what happened was that this experiment represented a big leap in science, in the field of quantum communication, a major one. And by December, President Trump, who is not very well known for a supporter of science and education, immediately authorized an initiative of $1.2 billion, which has now gone on for over $4 billion in the United States. And the whole notion was to really compete well with China. So quantum computers leverage exotic phenomena, etc., highly secure communication, and China, which has been investing heavily in quantum technology, so now the United States has to match that. And that was the motivation behind it. And of course, very soon, European Union followed with an initiative of its own. And now, quite frankly, wherever I go in the world, I was in Turkey last week, and they were talking about a major initiative in quantum technology in Turkey. And I come to Pakistan, and of course, people are very interested in this technology. So this is really something which has brought about, actually put the seeds of a big science revolution in the coming generation. The physics community became aware, of this major input, and this all was represented by this article, which many of you may not see from behind. So this was an article which was published by the Physics Mouthpiece in the United States, American Physical Society, Quantum for All. And I don't need to show you the names of the authors. There are three authors of this article, but more important than the authors are their affiliations. So the first author, Irfan Siddiqui, he is a professor at University of California at Berkeley. The second one, Dario Gil, he is with the industry, IBM Research. So university, industry. And the third author, Joseph Broz, he is from Quantum Economic Development Consortium, a politician. So basically this is an article which is written by three very different areas of interest, university, industry, and government. And they are basically promoting this idea that somehow this technology, if technology is going to touch the lives of millions or more, then the quantum mechanics must transition beyond a specialized physics course to a core requirement. So what they are talking about it is that just like an elementary student is expected to know something about Newtonian mechanics, a situation should come in if quantum technology has to become the order of the day, then some basic knowledge of quantum mechanics should be imparted at a lower level. Quantum mechanics at this point happens to be the introductory course is part of the curriculum at a much higher level, grade 14 or grade 15, for example, in our education system. So what they were talking about is to introduce it at a much lower level. Well, in my boastful moments, there are very few things to boast about, but one of the things I always claim is that in some sense I was ahead of these developments, in the sense that in 2017, I proposed to teach a course in quantum mechanics to freshmen, students just out of high school. And the procedure in my university is that if you want to teach a new course which has never been taught before, so you make a proposal, and the department, there is a body there which approves that course. So I did just that, and almost always they accept it, you know. But in this case, they unanimously rejected it. They said, Dr. Zubairy, you just don't know the background of these high school students. They're, you know, it's just not possible that you can offer a course to these freshman students who have not studied calculus, I mean, no background in calculus whatsoever, very rudimentary background in algebra, and very little background in physics. They have not taken the college level basic physics courses yet. But anyway, I somehow argued and prevailed, and I offered a course. And then this course was based upon these ideas. So I talked about the fundamentals of quantum mechanics, and then I talked about fundamentals of quantum communication, quantum computing, and so on. Schrodinger equation, as you can see, which happens to be the first lecture in a usual quantum mechanics course, happens to be the last lecture or lectures, because you know, the rest of the course is entirely algebra based. Okay, and it turned out that the course was very much liked by the students, and a proposal came that perhaps I should convert my notes into a book. So that is how this book came out, and it was published in 2020. Okay, so now let me start my lecture. I don't know how much time I have taken. So this is a very special year, and this is a very special occasion from that point of view. This is the 100th anniversary of quantum mechanics. Tomorrow I give a lecture at PIAS where I will basically discuss what led to the invention of quantum mechanics. What were the events which really were nudging in the direction of quantum mechanics, okay, which eventually a 24-year-old Heisenberg eventually formulated with some ideas that still baffles people. And I'll mention that in my lecture tomorrow at PIAS, that how come, you know, what was Heisenberg thinking when he came up with these ideas about quantum mechanics. So this is the 100th anniversary of quantum mechanics, and this was the paper which was, here is the beginning, and so this is the English translation, but the very first sentence of that paper is here. The present paper seeks to establish a basis for theoretical quantum mechanics founded exclusively upon relationships between quantities which are in principle observable. So Heisenberg was in some sense trying to derive a mechanics which would describe only the observable quantities, not dealing with those quantities that were unobservable. And this sentence, in some sense, is absolutely remarkable when one thinks about it, because most of the foundational issues that come in quantum mechanics are rooted in just in this sentence. I mean, this sentence haunts us to this day. But this is not what I will talk about today. There's probably some ideas about it I'll talk about tomorrow. Today, as a matter of fact, I go back to something which is very close to the founding. So quantum mechanics was invented in the summer of 1925 through the work of Heisenberg. And one of the founders of quantum mechanics, and again it's a very interesting episode, how Paul Dirac, he almost reinvented quantum mechanics and really went very far. He played a very important role in laying the foundations of quantum mechanics. And not only that, but in 1930, barely 5 years after Heisenberg's paper, he wrote the first textbook on quantum mechanics, which, if we think about it, is astounding. that he could put together. And this book, after almost 100 years, 95 years, is still a very relevant book. I mean, still, when we read it, we appreciate, the depth of knowledge in this book. And this book also starts with these notions. So I mentioned that on page 1, the need for quantum theory. The page 4 happens to be the polarization of photons. Okay, so he's talking about polarization of photons. He's essentially opening the book with polarization of photons and interference of photons, etc. Okay, so these are the first few pages of this very first book on quantum mechanics. So, okay, let me see. So if I can read it from here, this shaded part. In our present example, the obvious experiment is to use an incident beam consisting of only single photon, one photon, and to observe what appears on the back side of the crystal. So this is a crystal which now we call beam splitter, on the back side of it. According to quantum mechanics, the result of this experiment will be that sometimes one find a whole photon on this side, and other times one will find nothing. And again, we will see that, as a matter of fact, this is a very mysterious behavior. I mean, it appears very normal to us now, but really the mystery of quantum mechanics is somewhat hidden in this very, very simple experiment. And then he goes on to say, when one finds a whole photon, it will be polarized perpendicular, and so on, so on. So my talk, the rest of my talk, will be essentially based on this system. Nothing more, nothing less. And what we will see is that how much physics, how much mysteries, how many mysteries we will observe just by understanding this experiment. Just this single photon on a beam splitter. And the whole talk, nothing less, nothing more, just based upon this system. So it would be a rather simple talk, but very far-reaching, very, very far-reaching consequences, as you will see. Okay, so here is my outline. So let me, since I've wasted so much time already, so let me continue. Okay, so this is the simplest system in quantum optics. Single photon from this side, no photon from this side. There is a beam splitter, and then after the beam splitter, there is an amplitude of transmission, reflection and transmission. So for a single photon input, this is what the transformation looks like. One photon on this side, no photon on this side, becomes now what we call a superposition of one photon on this side and no photon on this side, plus no photon on this side and one photon on this side. And these are the amplitudes. We call them amplitudes, cosine of theta. Cosine of theta represents something like the reflectivity. Its square becomes the probability of reflection. Okay? And similarly, sine square theta would correspond to the transmission. If we reverse it from 1, 0 to 0, 1, no photon here, one photon here, then the transformation property would look something like this. One of the crucial things is this negative sign. Okay? There is a phase shift. I mean, again, it has its origin in the conservation of energy, but I'll not discuss too much about it. So this is what we have. If instead of a single photon, we have an ordinary laser light, this kind of light that is here, in that case, the transformation properties look something like this. I'll not talk much about it, so I'll not dwell too much about it right now. Okay? But these are like classical type fields. Okay? How classical light splits. Part of, if there is a beam coming in here, part of it is reflected, part of it is transmitted, and so on. Okay? So that is this. But let's concentrate on this and move on. Okay? First of all, even at this point, the thing which is very mysterious is that here is a single photon. Unlike a classical beam which splits, part of it goes this way and part of it goes this way, here it is a single photon. Either it goes this way or it goes this way. What determines that it will go this way or this way, we do not know at all. This was the point
which disturbed of many eminent people, particularly Albert Einstein. I mean, this is the root of this probabilistic nature of quantum mechanics. What tells the photon to go either this way or this way? Quantum mechanics can give you only the probability that 50% chance is that it will go this way, and 50% chance is that it will go this way. But for a single photon, quantum mechanics has no prediction. Okay? And this is something which Dirac is referring in his opening remarks of the book, that this is really a very big mystery, and this is a mystery which would haunt the physicists for a long time. There was a major debate in 1935 between Einstein and Bohr and Schrodinger got involved, and they were discussing the consequences. And this debate is still in some sense unresolved. In some sense it is resolved, but not, for some people it is still to be debated. Okay, now let's move on. So let's consider, let's say, not a single beam splitter, but two beam splitters. So that this photon comes in, part of it is reflected, part of the probability is that it is transmitted. There is a mirror, gets reflected, and then this, if it is reflected, then it is passing through this beam splitter again. Part of it is reflected, part of it is transmitted, and same thing goes here. The transformation properties are given here. So we can do a very, very easy calculation that initially we started with 1, 0, and after the first beam splitter, it is something like this. 1, 0 transforms into these amplitudes. And then the mirrors come in, and after the second beam splitter, if this is the amplitude 1, 0, then it transforms like this, and if it is 0, 1, it transforms like this with this negative sign. We combine them together, and this is the result we get. Okay, this is one of the very few mathematics that I'll discuss in this lecture, but this I just show for you, because this we will use. Okay, so this is one situation. So right now I'm not discussing any further, just giving you a mathematical result. The second situation that I discuss is what happens when we block the path on the right-hand side. Okay, we put an object here, which is an absorber. The photon, if it goes in here, will be absorbed. So then what happens is just after the first beam splitter, at this point, we have this superposition of the photon on this side and the photon on this side. But if it is on this side, this contribution, this basically gets absorbed. Okay? So this is what we have. And then the second beam splitter, basically, this amplitude goes in, cosine theta, and this 1, 0 undergoes that same kind of transformation as here. And then it goes to the second, it gets partly reflected, transmitted. So we get this probability of click at D1 and click at D2. Okay. And if I add this probability plus this, it should be equal to 1. There is only one photon. So either it will end up here, here, here. Okay. Just this. Okay. I will not use any more mathematics. Now the rest of the story will be told in terms of pictures. Okay. So, but we need to really understand what we just did, and this is very, very simple. As you can imagine, not many things could be simpler than this, really. But let's understand the consequences. Okay, so let's consider now these two results that we obtained, and consider a special case of a 50-50 beam splitter. That means that this theta, cosine theta, this should be equal to 1 over square root of 2. That means theta should be equal to 45 degrees. Okay? So in that case, reflection and transmission, they are 50-50 probability. Well, if this is 45 degrees, then cosine of 90 degrees is equal to 0. So we have 0, 1. So in this case, interference dictates that the probability of click at D2 is unity. Okay? Whereas in the other case, what happens is that there is no interference. This amplitude comes in, half of it goes this way, half of this goes this way. So 50% is lost here, and the rest of the 50% will give us a click with 25% each. Okay. So this is looks very innocent results. Okay? But now when we start analyzing them, we see almost mind-boggling result in just this very simple example. One of the things that we notice is, and this was noticed already going back in 1993 by Elitzer and Weidman, and that is that if we have a click at, so in this case, we get a click at D2 with unit probability. In this case, we get a click of 25% at D1 and 25% at D2. So if we get a click at D2, then it could be either this one or this one. Okay? I mean, here it will, if this object was not there, then it will definitely get us a click. If this object was there, then there is a 25% probability we get a click here. Okay, so we cannot conclude anything by just looking at this click whether the object was there or not there. But just imagine those events where D1 gives us a click. In that case, what we will see is, what we'll conclude is that this is only possible if there is an object sitting here. Okay? It cannot be this situation. An object must be sitting here when we get a click, in those events when we get a click at D1. Okay? Now let's see how we observe an object. How do you notice that I have a pen in my hand? The way you see the pen in my hand is because the light from there is coming, hitting this pen, and then reflected into your eyes. So light has to somehow interact with this object or get reflected from this object in order for you to see this object. Is it possible to see this object without light ever interacting with this object? You see without seeing this object. Conventionally, classically, it is impossible. You need to have something interacting with this object in order to see this object, in order to present its detection. But this is precisely what is happening here. I mean, if I get a click at D1, there is only a single photon. The only way the photon must have traveled is this path. But this path does not involve the object. So in this case, what we will infer the presence of the object without the photon interacting with the object. So this is quite a remarkable result. So this is what is referred to as interaction-free measurement. Okay? So this is something which one could obtain from such a simple circuit. Now let me also discuss another very important thing, almost going to the foundations of almost our existence. This is a very big statement, origin of our existence, or the origin of the universe, those kind of questions, just from this example that I just presented to you. How? So essentially here we are talking about this famous question of reality, which was addressed from this podium by the person who introduced, and that is, can we, our objects, is the universe around ourselves is real? So the first thing that we have to define is, what is the definition of reality? A definition of reality is an object can be considered to be real if its existence is independent whether we look at it or not. So all the world outside, the car that you came in, the transport, the road, the traffic, the Parliament House, we think they are real. The moon, the sun, none of us is looking at those objects. But if somebody tells us that they existed only when we went outside and looked at them, and when we entered in this room, they disappeared, they did not exist, would sound like crazy. Okay. So the definition of the reality is that it exists independent of whether we look at it or not. This is ingrained in us. Things exist whether we look at them or not. Whether we close our eyes or open our eyes, doesn't matter, they exist. Okay? So picking up on a famous phrase by Albert Einstein, we all believe that moon exists when none of us looks at it. It is hard to imagine the reality of an object like moon depending on us directly observing at it. If somebody says, oh, moon doesn't exist right now because none of us have any means of seeing its existence, that would sound ridiculous. Okay? So we all believe in moon's existence. But it turns out that quantum mechanics seems to deny the existence of objective reality. And I mean, as we can imagine, this would be stunning, really stunning if it is true. So from what we have just learned, can we get an answer to this question? Okay, so this is what I show you next. Okay, so this is a version, a very simple version of something which John Wheeler had proposed many years ago. So let's consider the setup that we just talked about. Okay? So this is what we call the Mach-Zehnder interferometer that we discussed, a beam splitter here and a beam splitter here, and these two detectors. What we found a few minutes ago was that if there is a single photon from an object coming in, going through here, there is a 100% probability, certainty, that I'll get a click at D2. Okay? So this is what we just saw. If this beam splitter does not exist, then there can be this scenario or this scenario. Now in this case, the reason why we get a click at D2, because at any given point between these interferometers, the photon happened to be in a superposition of these two paths. In some sense, the photon is in a very incomprehensible way, is traveling through both paths and combining together at this beam splitter and giving us a click at D2. Let's look at this one. So in this case, there is no beam splitter, the second one. So in this case, if the photon came in here, I'll get a click at D1, and I'll conclude that the photon traveled all the way through this path. And if the photon could also get reflected, and 50% probability, and I get a click at D2. Okay? So in this case, if I get a click at D1, I will conclude, since there is no beam splitter, that it followed this trajectory. And if I get a click at D2, I'll conclude that the photon followed this trajectory. Okay? Very simple. There is no mystery at all. Okay? Nothing could be simpler than this. Okay? But now for a moment, let's assume that this distance from here to here happens to be 1 light year. This is some kind of a star which generated a photon, and somehow, in our thought, mind experiment, we see that this is, this is traveling. There is a beam splitter traveling, and then it takes 1 light year. So 1 year ago, the photon started its journey. Now this morning, it is about to reach us here. Okay, we are sitting here. And now at this point, photon had been traveling for 1 year. We were sleeping at night and working during the day, not worrying about what photon was doing. But this morning we expected the photon to arrive. So we had to make a decision. Either we put this beam splitter here, or we do not put the beam splitter here. Okay? If we put our beam splitter here, then, and put this setup, D1 and D2 detectors, then this detector will definitely click. Okay? And what we will know is that photon for all these years, all the year long, it traveled in a superposition of these two paths to get to us and give us a click at D2. But if at this morning we decided not to put the beam splitter here, then we will get a click either at D1 or D2. If I get a click at D1, then I will conclude that for the whole year, the photon traveled through this trajectory, on this side, right-hand side. And if I get a click at D2, then it traveled all these years to the left side. Okay? Now this, if you think about it, it's a very, 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 very mysterious result. What is happening somehow is that our decision to place this mirror here, beam splitter here, or no beam splitter here, okay, basically decides whether the photon passed either through the right path or upper path or the lower path. Okay, if we decided to put no beam splitter, then it will be this. So it will be just single path. It could be this one or this one. But if we decided to put the beam splitter, then interference took place, and in that case, photon passed through both this and this. It's not and this or this, it would be rather this and this. Okay. So now what has happened is that what we did this morning changed the trajectory of the particle for the whole year, the past year, 1925, 24, 25. Okay. How can that be? What we are doing today is changing the past, the trajectory of the photon. If we take this argument a little bit deeper, then we can say that the entire history of the universe from its beginning depends on what we are doing now. Now this looks very, very strange. Okay? I mean, how can what we are doing now determines our past? I mean, what we have been taught and what we have believed all along is that past is past. We have absolutely no control in going back into the past and changing it. But this very, very simple experiment is telling us that no, that is not true. We can, as a matter of fact, go into our past by doing something in the present. Okay. So this is quite a remarkable result. So this is one position that we can take, that our present changes the past. So the founders of quantum mechanics, by considering similar kind of examples, could have concluded that. But instead, particularly Heisenberg and Niels Bohr, I mean, they came up with this notion about reality. Basically, they denied reality. They said that actually this is too much, that my present, what I do present changes the past. What is more reasonable is to, which is by itself also very, very strange, and that is to say that as a matter of fact, the trajectory and even the photon had no existence until it was observed. Until we put this detector, the photon or the path itself had no reality associated with it. So this would seem to imply that until we make an observation, there is no reality. Okay? So this is the position which is believed by most physicists, but still, if you think more about it, and actually in some sense experiments have supported this point of view, something I don't have time to talk about here, but it is a very stunning result if this interpretation is true. Any interpretation that you take, experimental results, there is no question. But how do we interpret these results? Do we assume that present changed the past, or there is no reality? It's our pick. Okay. But and then we have to really think more harder to come up with to come up with more experiments to show which one could be correct. Okay, so this gives us some idea about all of this. Now let's make system somewhat more complicated. What is happening? Can you? Okay, so now let's make the situation slightly more complicated. Okay, so I started with one beam splitter, then I had two beam splitters, now I have n beam splitters. Okay, Sajid, how long do I go? It's no, I can continue talking for hours if. Oh, okay. No, it won't go that long. So, okay. So now let's make things a bit more complicated. N beam splitters. 1,
2, 3, and then there's this dot, 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 capital N. So now there are n Mach-Zehnder interferometers, and this reflectivity now is accordingly smaller. It goes like pi over 2n. When n was equal to 1 or 2, then it was pi by 4. But now it is pi over 2n. So n has now two meanings. One is corresponding to the reflectivity, cosine of pi over 2n, and capital N is also the number of these Mach-Zehnder interferometers. Okay? So now we can just apply these formulas that I mentioned at the very beginning. My talk will be just based upon these equations. When I keep doing that, then it happens that after n cycles in this situation is cosine of n theta, but theta is equal to pi over 2n, so capital N times theta is equal to pi by 2, cosine pi by 2 is equal to 0, sine pi by 2 is equal to 1. So I get with certainty detector D2 clicks. Okay, so in this configuration, detector D2 clicks. Now, what if the photon is blocked at each stage? Okay, so now we have generalized to n Mach-Zehnder interferometers. So in this case, again, we keep doing the same thing, that that part of it is reflected, part of it is transmitted, transmitted is absorbed. The reflected part comes in, part of it is transmitted, part of it is reflected, transmitted part is absorbed, and so on, so on. Okay, so then I get a click with almost a unit probability. So there is a little mathematics here, but you know, the mathematics is very straightforward. Just these transformations, and what happens is that in this case, D1 clicks with almost unit probability if I make this n large. Okay, okay. So this was again some equations. But now let's summarize these results which are mentioned here, that if in this kind of a setup of n Mach-Zehnder interferometers, there is no blockade on this side, then I get a click at D2 with certainty, with unit probability. On the other hand, if I have a blocker, I put my arm in front of all these mirrors, then in that case, the photon will be detected at D1 with almost unit probability. Okay. So this is now the result. Okay. So now what is the use of these results? So this was first of all an experiment which was done by Anton Zeilinger and his group, Paul Koyat and so on. Zeilinger, as I mentioned, won the Nobel Prize a few years ago. And he basically talked about this setup showing that one can have interaction-free measurement with almost unit probability. Okay. So this was an experiment which was done a long time ago. Please, at some point I'll remind you Anton Zeilinger as one of the co-authors of this paper. Okay, but not now. So he was, this experiment was done in his lab. Okay, so now this idea, very recently, this paper appeared, as a matter of fact, just end of 2024, a few months ago, and that was the deterministic generation of a Schrodinger cat state. I should have a cat state. So let me just very briefly mention what is a Schrodinger cat state and what was the motivation and how do we generate in a lab. Okay. So essentially, Schrodinger cat state was a notion which was introduced by Schrodinger in 1935, and the motivation of using this notion was absolutely remarkable. Here was Schrodinger, who was the founder of quantum mechanics. His equation, the whole book of quantum mechanics, start with Schrodinger equation, and one example after another. And what Schrodinger, he wrote his equation in 1925, few months after Heisenberg's work. But in 1935, he was so disgusted with the results of quantum mechanics that he wants to disprove quantum mechanics to be right. And this was his attempt. Okay. So let me first explain what Schrodinger cat state is and what was Schrodinger's actual motivation of introducing this in his own words.
So basically, the idea of a Schrodinger cat state is this, that there is a cat, an alive cat is placed in a steel box, completely unable to interact with outside, and there is a Geiger counter, a radioactive substance, a hammer, and poison in this configuration. Okay, so now what happens is, according to Schrodinger, that this radioactive matter or radioactive atoms, they can decay randomly. I mean, we only know their half-life, but we do not know when they will decay. Okay, so when the radioactive atom decays, then it emits a particle, alpha particle or beta particle, depending upon what material we have. It actually hits the Geiger counter. This is a counter. We don't need to know the details. This counter, when it gets a click, it allows this hammer, triggers the hammer, and this hammer hits the poison bottle, releases the poison, and the cat is dead. Okay. So what Schrodinger is arguing is that there is a possibility that radioactive decay does not take place. It is there. In that case, cat lives. But if radioactive decay does take place, the particle is emitted, then it will hit the Geiger counter, which will trigger the hammer, which will break the poison bottle, and the cat dead. So we have now two situations in which radioactive decay does not take place, the cat is alive. But if the radioactive decay does take place, then the cat is dead. So at a given point, we have something like an entangled state with some amplitudes that no decay takes place and the cat lives. Decay takes place, cat is dead. So now Schrodinger argues that, so I hope this is understood. But now let's understand why Schrodinger was talking about it. Schrodinger's argument was that this quantum mechanics is ridiculous. And it gives, the results that we talk about are about atoms. An atom is in the ground state, an atom is in the excited state, an electron we talk about. But those are objects we don't see. But cat being alive and dead, this is something which we can see. If it is in front of us, we can see that it is, cat is alive and dead. So talking about an atom in a superposition of ground and excited state, this is okay. I mean, somehow, it's like ancient people. I mean, we associate a greatness with the people we don't know about. Immense greatness. But the same person, if he comes and stands in front of us, the whole image tends to disappear. Okay? So the things which we cannot see, we can create myths around them and pretend to understand. But the thing which is in front, which we can see by our eyes, there the standard of reality is much higher. Okay? So the cat, so for atom, quantum mechanics could be okay, but not for a cat. We do not see a cat which is simultaneously alive and dead. We do not even know what it would mean. But of course, when we observe, it is either cat, dead or alive. So this was his motivation of introducing Schrodinger cat state. Let me see in his own words. So these are his own words, written in a paper in 1935. That one can, this is what he is writing. And look at the sentence. One can even set up quite ridiculous cases. This was not my word, this was his word. He, the inventor of quantum mechanics, was so unhappy with the conceptual foundations of quantum mechanics that he wants to set up an example which proves how ridiculous it is. Okay. We never do that in our life. Our own creation is the most precious thing, and we want to preserve it. But here Schrodinger is showing his complete dismay. Okay, so he sets up a ridiculous case. A cat is penned in a steel chamber, etc., what I just described. And it is a typical of these cases that an indeterminacy, probabilistic nature, originally restricted to the atomic domain. So there, since we cannot see the atoms, at least in his time, one could not see the atoms, so it was okay, becomes transformed into macroscopic indeterminacy. I mean, uncertainty associated with a big object like a cat. And that does not look right. The things that we associate with atoms, somehow we cannot associate with a big object like cat, okay, which can be readily observed by direct observation. Okay. So this was his motivation. Of course, the people, Heisenberg, Bohr, and so on, Max Born, they were quite comfortable with quantum mechanics, with its interpretation. Some of it I mentioned to you. But people like Schrodinger, I mean, one big person on his side was Albert Einstein. And just see how Einstein patted on the back of Schrodinger. So this is a later collection of the letters, but the letter was written when Schrodinger sent him his paper in 1935. So Einstein basically is patting on Schrodinger by saying, you are the only contemporary physicist besides Maxwell's law, probably some of you know the name from crystallography, who sees that one cannot get around the assumption of reality if only one is honest. Most of them, them means Bohr and Heisenberg and Born and Dirac and so on and so on. Most of them simply do not see what sort of risky game they are playing with reality. Reality as something independent of what is experimentally established. So you can see in 1935 this discussion, very serious discussion about the nature of reality. And there was almost a very clear split. The wave theory people like Schrodinger, de Broglie, Einstein, and so on, and the matrix mechanics people. Matrix mechanics I call the theory which was developed by Heisenberg, Bohr, Born, Dirac, Pauli. So they were on the other side as far as this conceptual foundations issues were concerned about the questions of reality. Okay. So, but now, since 1935, people have actually tried to make objects in two states, not necessarily the cat. Cat would be very difficult to emulate. But objects where you see a huge object in two different states simultaneously. Okay, and we got involved in this project only 2 years ago when I realized that, as a matter of fact, as far as the radiation field is concerned, there is hardly any scheme where one can have Schrodinger cat state. As a matter of fact, what I discovered was that in 2019, a paper was published by somebody who is very, very famous in quantum optics, Gerhard Rempe, and he, through this kind of a setup, I don't have the time to discuss it, but he created a cat state, a Schrodinger cat state of a coherent state with different phases. Okay, so coherent state, this alpha represents, alpha square represents the number of photons. And the only state that they could prepare was with just less than 2 photons. Now that is not quite a Schrodinger cat state. Schrodinger cat state would be if there are 10 or 100 photons in this state or this state simultaneously existing. Okay. So what we did was, and again I won't discuss it very much. So we came up with this idea using this kind of a scheme which I just talked about, by using this kind of a scheme which could be implemented in this kind of a setup by showing that, as a matter of fact, one can have a Schrodinger cat state with as many photons as you like. So that would be a real Schrodinger cat state And this experiment, I mean, this results we published just a year ago. So I hope this experiment is done, and a true Schrodinger cat state would eventually be established in the lab. But this cat state is not cat. It is this light, so very strong light in this state or this state. Okay, so this is sort of some details. So I'll not go into it. May take more time. Let me actually jump to something that we did a while ago, which is now the next complication level. Okay, so far we talked about single beam splitter, two beam splitters, n beam splitters. Okay. Now we come to capital N times capital M beam splitters. And this scheme, which was proposed by us in 2013, a lot of discussion took place. I mean, we were bitterly criticized in the literature. How can it be? Okay, because we were challenging some ideas that had existed for thousands of years. So if something that we have believed for thousands of years, and now a paper comes along and says there is a possibility that it can be violated, of course it can create a lot of sensation. So this is what happened with this work, which we originally published in 2013. A graduate student, this is Senghong Li. He was my postdoc at that time. He is now professor at Shanghai University, a very colleague from Saudi Arabia, and we did, we did it in 2013. And we have actually, between these two papers, we have worked many different schemes of different kind of things. Okay. So let me just quickly talk about it, what the problem is. Okay. So the problem is, okay, so let me just give you the schematics. The schematics is that Alice and Bob want to communicate with each other. And modern communication actually is always binary, 0 and 1. Any communication that we have electronically, that is always in terms of binary numbers, zeros and ones. Okay. So the way it is set up is that Alice has a source of photon. So she sends a photon. This box represents some ordinary optics. I'll give you the glimpse of it in a moment, that it is very simple optics. Bob is far away. So if we are here in Islamabad, Bob is in Lahore, let's say. Bob has no optics except for a mirror. Okay. So now what happens is that Alice sends a photon. Okay. And Bob has only a mirror. And what Bob can do, if he wants to send a 0, then he would put his hand in front of the mirror. Okay. So there is lab, there is optical fibers coming in. Bob has a mirror, so Bob puts his hand in front. That would correspond to a logic 0. Okay. When he does that, then Alice's end, which could be in Lahore, the detector D1 clicks. So when detector D1 clicks, she knows that Bob blocked and he wanted to send a 0. Okay. The second option for Bob is Bob doesn't do anything. No blockade. There is a mirror, photon can come and go. In that case, what happens is that detector D2 clicks. So when detector D2 clicks at Alice's end in Lahore, she would know that Bob wanted to send a logic 1 by not placing his hand in front. Okay. So far there is no magic. Okay. So you can set up something like that. The magical thing is that in both these instances, in this instant and in this instant, the photon basically bounces back and forth in this box and give a click at D1 without leaving this box. So photon is not in this channel. Similarly, in this case also, depending upon what Bob does, this photon basically bounces back and forth and give a click here without leaving this box. So this is very mysterious. This is not how we perceive communication. Our idea of communication for thousands of years is that something should exchange between me and you, like fiber optics. photons are being sent from here to there. Electrical conversation, speech. These molecules are creating a wave and hitting your eardrums and so on. It cannot happen that something that you do and there is nothing in between and I can find out what you did. If I could do that, there will be a non-scientific words for it, like psychic communication. But we all know psychic communication, even though a lot of people, that is not science at all. Okay, that is not science. But okay, but here we are talking about some system which acts like like psychic communication. The photon never left this box or here, yet it senses. Alice can sense what I did. Put the hand in front or no hand in front. How can that be? Okay, I mean, this is in some sense going beyond the paradigm of communication that had existed for thousands of years. Okay, so let's try to understand it. And it turns out that the ease, I mean, if you understood what I talked about so far, these different beam splitters, if you understood that, I can at that level make you understand this whole thing. It's so simple. Okay, so let's do that. Okay, so now we make a system slightly more complicated. One beam splitter, two beam splitters, n beam splitters. N beam splitters. But now we make n times m beam splitters. One is going one stop beyond. How? So we have now these m beam splitters, okay, and in such a way that on the left-hand side is like any beam splitter, any interferometer. But the right-hand side, we put these n Heisenberg interferometers in each one of them. In each of these m's, this dot 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 means there are m of these, capital M of these. So there are m of these outer ones, and inside there is this whole thing. Okay. So now the setup is such that in this setup, everything, all these beam splitters, this one, this one, this one, these mirrors, these beam splitters, everything belongs to Alice. Then there is this public channel, and on the other side are these arrays of mirrors only. So Bob has only access to these mirrors. Everything else belongs to Alice. Okay, and now Alice is sending a single photon. And the question is, which one will click and what information it will give us. Okay. So let's set up the problem in such a way that if Bob, there is Bob sitting here, wants to send, does not block at any stage, he is trying to send a 0. If he blocks at every stage, he is trying to send 1. Okay. Now let's see how this will work. Okay. So let's do. Okay, this is the reflectivity for m photons, m beam splitters, and so on. Okay, so now let's concentrate for a moment. This is what we had found out, that in this setup, if there is no blockade, then I get a click at D2 with certainty. If blockade at every point, then I get a click at D1 with almost unit certainty. Okay, so this we learned. Now we use this learning into this setup. Okay, so now what we see is that if the photon is sent here, okay, then it can get reflected or it can be transmitted. But if it is transmitted, then it faces a situation very similar to like this. Okay, these are n Mach-Center interferometers. I don't have to do any calculation. Just this picture tells me that in this case, it will end up here with unit probability. It will end up here with unit probability. It will be lost. There is only one photon. So it will be lost. Okay? So essentially, this part is acting like this absorber. Rather complicated looking, because if the photon comes on this side, then it will be lost. Okay? So therefore, the situation overall is something like this, and there is a large probability that the click takes place at D1. But please notice, and now this is a very important point, please notice that if I get a click at D1, the photon could not be on this side, on the right-hand side, because if it happens to be on the right-hand side, then it will definitely give us a click here, and it will be lost. So the photon can only carry out this trajectory, the outer one. It can never be in this region. Particularly, it can never be in what I call public channel. Okay, so in this case, there is zero probability for the photon in the public channel, because if it happened to be in the public channel, then it will be lost here. Okay? So this is one scenario. Now let me consider the second scenario, when Bob puts a blocker or an object in front of these mirrors for all of them. Okay? So now in this case, we can see that the H.I.S.I photon, when it comes here, it encounters something like this. Okay? This whole setup is something like this. But here what we learned was that at the end, with almost unit probability, the photon will go on the other side. The photon will go on the other side. And what is happening is that this whole setup is almost mimicking this thing. So the actual situation is something very similar to here, because in this case, whatever amplitude comes in here goes into the second one. But please notice again that in this setup, I'll get a click at D2 like here, but the photon will never be found in here. Because if photon is found in the public channel, then it will be absorbed. So now we have, so in this case, we can, Alice can conclude that Bob wanted to send a 1, but there is no photon in the public channel. So now, if we combine them together, what we see is that this is a situation where the click at D1 takes place, but the photon is not in the public channel. So we know that Alice wanted to send, Bob wanted to send a logic 0. And in this case, it would be click at D2, Bob wanted to send a 1, but there is no photon in the public channel. So in both instances, the photon is not in the public channel, yet this Alice's photon goes back and forth and gives us a click at D1 or D2, depending upon what Bob is doing. Now this was something so remarkable that some people just refused to believe. And just 3 days ago, I was invited to give a lecture in Turkey, and I gave the full history of how, when we published this paper, what kind of opposition we faced, because people just thought this could not be true. And I still remember once I was giving, in 2014, I was giving this talk in front of an audience that included Zeilinger and some 2 or 3 other authors of that famous paper. And Zeilinger literally held his hand like this. And basically what he said was, why didn't we think of it? Because they went this far. It was just a question of putting this outer interferometer to get this almost unbelievable result. So it's created a lot of controversy. So, I mean, the possible implementation that we suggest is not this one. This is easy to understand, very easy to understand, but difficult to implement, because a lot of optical instruments are required. This would be the possible implementation setup with some very simple optical instruments. Okay, so this work was experimentally implemented by none other than one H.I.S.I FPAS. Remember in the first slide I mentioned this 2018 paper and so on, and this was actually the implementation of it was done in 2017 by this H.I.S.I FPAS and his group, and he talked about intuition from our everyday lives gives rise to the belief that information exchange between remote parties is carried out by physical particles. Surprisingly, in a recent theoretical study by us, he mentions our paper, quantum mechanics was found to allow for communication even without the actual transmission of physical particles. So this was, and they did the experiment. Okay. Again, there is some history behind it, which I don't have time to tell. And then this paper was regarded as the 2017 breakthrough paper of the year. A lot of controversy was involved. People did not believe that this could be true. And the arguments that they advanced did not hold much water. And sometimes this controversy became very, very tense, I should say. But then in 2020, there was a paper by Aharonov and Rohlik, Yakir Aharonov. Many of people in this room would recognize Yakir Aharonov. If somebody, I mean, if there is a title, the most greatest scientist, living physicist today, he would be on many people's list, Yakir Aharonov. He is known for Aharonov-Bohm effect. This is what he wrote about our work. So this is how the paper is started, actually. This is how the paper is started. And he talked about us, describe a remarkable effect which they call counterfactual quantum communication, transmission across a transmission channel of information from a sender to a receiver without any physical particles traveling between them. For all our familiarity with quantum non-locality entanglement, the effect is startling. It involves neither non-local quantum correlations, which anyway do not transmit information, or the relative phase of Aharonov-Bohm effect. And who is writing this? Aharonov himself. If any effect evokes Einstein's famous phrase, spooky action at a distance, it is this one. So this is, I think, the end of my talk. Yeah, one thing I would like to sort of advertise, and that is that this is the book which I wrote for my freshman course, and many of this discussion that I presented here is contained in here. So, you know, the level at which we can understand many of these things are such that even high school students can understand that. And then motivated by that, I wrote another book which subtitle is a mysterious universe. Subtitle is Quantum Mechanics, Relativity and Cosmology for Everyone. Everyone means anybody who does not have any background in physics or mathematics should be able to follow. Of course, I cannot guarantee that people will do that, but my intention was to write a book along those lines. So I don't know how available these books are here. I brought some very few copies, 1 or 2 copies for each one. Again, it would be a very tough job of who to present it to. But I'll seek some help from my host. Okay, with that, I thank you very much. It has been my great honor to be here and be hosted by someone like Dr. Sajid Qamar. I take great pride in the fact that I produced students sitting in this country, which is very important, who have gone on to not only great administrative positions like what they are here, but have also continued to do really good work, research work. For example, when I was in Turkey just 3 or 4 days ago, one of the professors there came to me and he mentioned that there was a postdoc with him from Pakistan, and his name was Shakirullah, and he did his PhD in Pakistan with one of your students, and I was immediately curious who he did his PhD with, Dr. Fazal Ghafoor. So, you know, I mean, when you have instances like that, as a teacher, as a professor, I mean, after all, I'm a human being, I feel great pride. And it has been a great honor for me to be here. Thank you.